Semiconductors. Today I'll be taking you all on a small journey, a very small journey into this massive world of semiconductors. Before I begin, as you all know, this talk is targeted towards PU students, first PU or second PU. Keeping that in mind, I'll try to cover the topics uh, with basics as much as possible so that it will hopefully help them in order to make a career choice in the future. So you can be from any science stream, PCMB, PCMC, PCME, doesn't matter. You just have to be a science student to get an overview of this. All right, so let's see what do we have in store today. Um, Firstly, I'll be giving a brief talk about how important electronics is and what are its applications. Later, we'll be talking in detail about semiconductors and VLSI. I'll be discussing what exactly they mean. Then I'll be taking you through the life cycle of an IC, and finally we'll be concluding with what are the opportunities that you can find in this industry. So, yeah, all right. Before we actually jump into what semiconductors are and what this industry is all about, I'd like to emphasize on the point on how important the field of electronics is in our day-to-day lives. Neil deGrasse Tyson, who is actually an American astrophysicist and a scientist, he had once quoted that dreams about the future are always filled with gadgets. Because if we just observe around us, we are practically surrounded by electronic gadgets all around us. It can be our mobile phones, laptops, computers, printers, or home appliances like your microwave ovens or refrigerator or AC, washing machine, your smart watches, everything, right from very small things to a very big thing. We are just surrounded by electronics all around us. These are just the things that we see in our day-to-day lives. Apart from what we see every day, electronics finds its applications in various other fields as well. For example, automotive industry. The cars these days are becoming smart. You know, we have so many things like sensors and emergency brake system, cruise control, and lot of control of all the parameters inside the car. All of these are present right now in the car. The cars are becoming smart. That's because of the intervention of electronics inside the car. So it has a great application in automotive industry. And then we have applications in healthcare, hospitals. There are a lot of life-saving equipments, which are electronic devices. And then communications. I cannot uh, tell you how important this is. Uh, Communication is present everywhere, right? From satellites, telecasting, broadcasting, networking, your internet, your Wi-Fi, in defense, in communications finds a lot of applications, wherein electronics is giving a lot of emphasis. And entertainment industry, music or filmmaking or TV, documentaries, anything related to the entertainment industry is heavily relying on electronics these days because it's slowly going digital. And robotics, of course, we have a lot of applications in robotics. And then education, classrooms are becoming smart these days. There are smart classrooms. And of course, online classes, which have become very prominent these days because of COVID. And because we have the right set of electronic gadgets and the relevant things with us, we are able to have a seamless experience of sitting in a classroom and listening to the teacher, even from the comfort and safety of our homes, which is a very big thing. Thanks to electronics for that. And then agriculture as well. Slowly, the farmers are moving into smart practices to improve their yield. So all in all, electronics is a very fun, innovative, creative, challenging field, which is helping us, which is making our lives more easier actually. So post your PU, if you choose engineering and if you choose electronics as a specialization, electronics can be electronics in communication or electronics in electricals. There is also medical electronics and telecommunications, anything which has electronics as a base. There are multiple career options that you can go into. I just want to shed light briefly on a few things that you can do before moving on to the actual topic. So you can always get into core electronics or telecom industries, which fall under the private sector. These may include the semiconductor industry, about which I'll be talking about next, or it can be an embedded industry, or it can be PCB or RF antenna. There are a lot of options. Similarly, you have all of these in the public sectors as well, like government organizations like ISRO or DRDO, BEL, a lot of options. Of course, they have a procedure to get in. You have to write some entrance exams and all, but there are options in the public sector as well. R&D is a subject which not many people go into, but we are actually in need of good researchers and scientists. And I'm sure KSTA is also organizing a lot of talks, which is helping you in getting a various perspective of everything. So research and development is a very good option if you are interested in working on the core electronics subjects. And academics, of course. Teachers, we are in need of good teachers. The world is always in need of good teachers. Of course, we have very good teachers right now, but we need more. And the impact and the presence of learning with a teacher is completely different as to compare to what you can learn out of the internet right now. So we need good teachers. Academics is a great option. These four are actually related to the core electronics. Apart from that, you can always get into software development or in the service sector. Or you can also do a higher education. After BE, BTech, you can do ME, MTech, MS, PhD. There are a lot of options. So these are the options which you have if you take electronics as a career. If you want to take electronics as a hobby, there are options for that as well. I'm sure many youngsters here will be familiar with the Raspberry Pi boards. They would be doing a lot of innovative projects on that. And you would be making a lot of small electronic components by yourselves, or you can be a ham radio operator. So there are a lot of hobby involved in electronics as well. So yeah, moving on. Let's move on to our actual main topic of interest for today, which is the semiconductor industry or VLSI. Now, what is VLSI? If you have any time seen a PCB or looked at the motherboard at the back of a computer or any PCB for that matter, you would notice that there are these small black boxes which are found embedded inside those PCBs. And if you have ever wondered what those black boxes are, those are called integrated circuits or ICs. And VLSI is all about these ICs. And today I'll be talking about these black boxes only. Okay, before we jump in, let's brush up a little on the basics, right? What are semiconductors? Semiconductors are actually materials which have a conductivity between that of a conductor and an insulator. So how does it work? You don't do anything at room temperature, they don't conduct, they behave like an insulator. You supply it with some energy, the valence electrons in the outermost orbit, it will break from the orbit and start conducting, and it behaves like a conductor. So essentially, it's mimicking the operation of a switch. You turn it on, it conducts, you turn it off, it doesn't conduct. So the behavior of a semiconductor as a switch is extremely important in electronics because we need that controllability on our devices. We don't want things to always keep conducting, or we don't want things to not conduct at all. So we need that controllability which only semiconductors can provide. So commonly used semiconductor is actually silicon, which is abundantly available everywhere as silicon dioxide, or in plain words, sand. Um, so silicon is extracted out of sand. And there are other options in semiconductors as well, like germanium or gallium arsenide. These are not very commonly used. Most of the components that we see are made out of silicon only, but we have other options as well. So why do we go to semiconductors again? So they are extremely reliable. They have excellent controlled conductivity, like I mentioned earlier. They are low cost because it's easily available. It's extracted out of sand. It's very sorry. It's very compact and it's lightweight. And these are essentially the prime factors that we need in every electronic gadget. We want all of these to be present in our electronic gadgets, right? So these factors make semiconductors an ideal candidate to be used in the manufacture of almost all electronic components like transistors and diodes. So what happens when we put multiple transistors on one single unit? So an assembly of these components like transistors, which are fabricated as a single unit, are called ICs, integrated circuit, the little black boxes that we saw earlier. And VLSI stands for Very Large Scale Integration. Now, what do we integrate here? It is the same transistors which we saw. The transistors are integrated on a very large scale on one single component. So that's why it's called Very Large Scale Integration. And the design, development, and manufacturing of these integrated circuits or ICs is nothing but VLSI. So who works on VLSI? I mean, um, this is VLSI. So let's see who are working on VLSI. There are a lot of tech giants like Intel, Qualcomm, Broadcom, AMD, ARM, NVIDIA, Samsung, Texas Instruments, NXP. Recently, Google has also started its own VLSI branch. Along with this, there are a lot of service-based industries and a lot of startups as well. In fact, the company I'm working for right now is a startup. HQ is a startup. So there are a lot of companies which are working on VLSI, and it's a very promising field. Okay, so we learned what are ICs. Now let's see how they are classified. So the ICs are broadly classified into three categories. There are ASICs, which are application-specific integrated circuits. Now these are ICs which are manufactured for a particular requirement, for a particular specification. They are completely optimized and customized to suit only one particular requirement. For example, you might find some toys in the market which talk, right? Some talking toys. So they'll have only one small IC which does only that talking part. So like that, they are specific to one particular application. So those are ASICs. And they can support digital, analog, mixed signal designs. Mixed signal designs are a combination of both digital and analog. For example, I don't know if you have come across ADCs and DACs. That's analog to digital and digital to analog converters. Yeah, those are ASICs and these are non-reprogrammable. Once you program it as something, you cannot change it. These are ASICs. Then we have general purpose processors or microprocessors. These are the normal CPUs which we find in all computers. They are not optimized for any particular requirement. They can perform any operation. And yeah, they're not customized, like I said. Everything else is same as ASIC, but it's just not optimized for one particular requirement. It can perform any operation. And thirdly, we have FPGAs. FPGAs are field programmable gate arrays. Now, these are actually big boards, which are generally used only during prototyping. Now, what happens here is there will be a big board with an array of switches, and we program it to work in a particular requirement. We finish testing that. And once we finish testing that, we reprogram it and it goes back to the same state as it was earlier. So only FPGAs can be reprogrammable. Um, Let me give you an analogy for this, for making it more easier to understand. ASICs can be regarded as building a house. Okay, you have a plot of your own and you want to build an independent house, a house which of your requirements, of your necessities, completely customized to your needs. Yeah, that building a specific house for yourself, an independent house for yourself, can be regarded as an ASIC. Now, microprocessors can be these readily available apartments, right, which has everything you want, but may not be completely customized to what you want. You have everything, but you have to work around certain things. So those are that can be regarded as a microprocessor. An FPGA can be an empty hall or a film set. Actually, a film set is actually a film studio. Film studio will actually be an empty space. And when a film is supposed to be shot, a set will be built up. After the shooting is completed, the set is brought down and it again becomes an empty space. So that's exactly how FPGAs work. These are the three main classifications of ICs. Okay, moving on. This is a very important question. Why VLSI? Like I said, VLSI circuits are everywhere. All the applications which we saw previously of all electronic devices and applications it finds in various fields, everywhere you will find a VLSI IC present. So it's there practically, it's there everywhere around you. And it has revolutionized technology on a drastic scale. For example, if we take this image down here, which shows you a memory card to the left, which says 16 MB. A 16 MB memory card earlier, this is like few years ago only. Earlier used to be almost 1/4 the size of your palm, right? A 116 MB memory card. And to the right is actually a 128 GB pen drive, which is almost half the size of your finger. So this revolution has happened over a very short span of time, and it's it's unimaginable to see how much it has scaled and how much it has made our lives easier. So because of the revolution in this field of VLSI, we are able to have smaller, sleeker, power efficient, powerful, robust, and high speed devices. The best examples would actually be our mobile phones. Earlier, we used to have mobile phones the size of a walkie-talkie, and now we have our smartphones which can practically do anything under the sun. So this is what the revolution VLSI has brought out in the field of technology. Okay, let's take another example. This is actually the PCB of a smartphone, a slightly old smartphone, probably. So if we see, notice this, there's a large space to the right, which is not having any components. That space is actually for the battery. So upon looking at it, we can easily make out that the battery is taking almost 75 to 80% of the space. We have only around 25 to 20% for the other electronic components. The reason is battery technology has not evolved as much as VLSI over the last few years. What do we need in our phones? We need a phone which has a good battery, more mAh. We need good camera. It should, even if it has a bigger battery, we still want it to be sleek. We want it to be lightweighted. It shouldn't feel like holding a brick in your hand. And we still wanted to do everything, all the things. We want to play games, we want to chat, we want to call, we want to do everything, but still we want a smaller phone. So how is this, how can we make this possible, right? Because the space available for an IC is reducing, but still we want more and more computational capabilities out of it. So how this is possible right now is we are taking multiple ASICs, the small ASICs which I talked about earlier, and putting all of them into one chip. So we have, instead of like having a house, we are now building a locality on one chip. So what does a locality have? It will have houses, it will have a playground, it will have school, it will have a college, hospital, everything, right? So we are putting multiple things on one chip, and that is called as a system on chip or SoC. Because of SoC, we are able to fit in more and more things on one single chip so that we can save lot of space. And when I say we are putting more things, you would naturally feel that this might increase the area of the chip, because, right? Because we're putting in more things. So a chip which was probably this big will now would have now scaled into something this big because we're putting more and more things. But no, we have a complete system put on a chip which is as small as your fingernail. If you see this picture down here, this is actually a Qualcomm Snapdragon 865 chip, the new chip, which is actually as small as your fingernail. So we have an entire SoC placed on one small fingernail sized chip. How is this possible, right? So to answer that question, we have the VLSI industry is actually following the principle called as Moore's law. Now, Gordon Moore, the gentleman in the picture, he's actually a co-founder of Intel. So when he started out, he observed a trend in the way these ICs worked. And he quoted that the number of transistors per chip would grow exponentially, which will almost double every 18 months. So this trend is still working. It's still in progress. The number of transistors in one chip started from being in hundreds to few hundreds. Is my video seen? Okay, I'm assuming it's visible. The number of transistors per chip started with some hundreds and it went on to few hundreds and then it became thousands. And from thousands, it became lakhs. Now we have almost millions of transistors on one single chip. That is because we are scaling the size of the transistors as well as we put more and more onto a chip. So right now we have almost 5 nanometer sized transistors, which is very close to the size of an atom. It's that small, and we have millions of such transistors on a complex network sitting on one small chip, which is as small as your fingernail. Okay, so that was a small introduction on what this industry is all about. Now let me take you to through a life cycle of a chip. What happens there? So firstly, someone, usually a customer, comes up with the specification, a set of requirements. Let's take a small example here. I'm sure you might have studied about adders, half adder, full adder, and all. Let's take a full adder as an example here. So suppose the customer comes and says, look, I want something which will take in two numbers, add it, and take the previous carry also, and give me a sum output and a carry output. So this is the specification a customer provides. Once we get the specification, there will be someone called as a system architect. An architect will sit down with other engineers like circuit design engineers and logic engineers. Sorry. So they sit together and they bring out a system model as to how we should design this component to meet the customer's specifications. So with that modeling, we will get something called as a golden reference. Like I said, this is a full adder, which takes in two inputs. One carry input gives you the sum and carry out. That's simple. And once we have the golden reference in place, the architect and the other engineers will come up with the architecture definition. Now we want to implement a full adder, but how do we realize it? What we can do is we can take two half adders and connect them serially and connect the carry of both of them and OR them together and give it as carry out. So this will be our architecture. Now, once the architecture in place, then comes the design. So there are design engineers. I myself am a design engineer. So what we do is we implement the design as per the architectural specification. Now, because we are implementing a hardware here, there are special languages which we use, which are called hardware description languages. So using previously all the chips used to be done on something called as VHDL. Currently, majority of the chips are done using Verilog and System Verilog. So those are the hardware description languages. You will get to learn these things in your engineering. So using hardware description languages, we will design the hardware. Post this, it goes through verification at multiple levels because we want to check the intent. If the intent of the specification is met in the design. So at various levels, we perform verification. And once the verification is done, we have to convert it into a schematic. What is this? So the design which I spoke about earlier, where where we code it using a special language, those languages are still English-like language, which looks very similar to C language. But that's still an English-like language. It has not converted into a hardware. We are actually building a hardware. So there is a process which will convert this English-like language code into actual hardware gates, logic gates. If you see here, there are XOR gates, AND gates, and OR gates. So that conversion is called synthesis. Post synthesis, the output that we get is actually called as a netlist. So the post synthesis schematic netlist, sorry. So the post synthesis netlist is actually taken, and that will be our blueprint in manufacturing the chip. Now, once we have the schematic ready, we will be sending it to manufacturing in a fab. Fab is nothing but a fabrication unit, the places where the chips actually get manufactured. Like I said, the whole design starts with a speck of sand, a sand speck from which we extract the silicon from. So there's actually a very nice video which shows you how the speck of sand is used in bringing out one full chip out. Let me share that video here.
Humble sand. This is what the building blocks of the future are made of. But making them is a long process compromising a great many steps. First, the silicon dioxide in the sand has to be converted into pure silicon. After that, it is cut into wafer-thin discs. In Dresden, these raw wafers are 300 millimeters in diameter and less than a millimeter thick. In our clean room, up to 35,000 chips are then made from each of these discs. In numerous process stages, the wafers are given their characteristic surface structure. After coating with a photoresist layer, the wafer surface is exposed, developed, and etched. This results in the desired conductor structure. Such structures are hundreds of times finer than a human hair. Dopants are then implanted in the material to increase the electrical connectivity of parts of the semiconductor. In subsequent phases, this and other process steps are repeated until the entire layout of the chip has been deposited on the wafer. This involves heating the wafer to more than 1100 degrees Celsius. In some cases, up to 27 times. Up to 200 measurements are done, and up to 26 exposures. All in all, this can mean as many as 700 processing steps and 14 weeks processing time. Once this is completed, the microchip is assembled from as many as 30 such layers, like a mini skyscraper. Each layer has its own function. Interconnecting them makes the microchip highly complex. Semiconductor chips, the building blocks of our future.
I hope the audio was audible. Can someone confirm if the audio was heard?
GoDaddy offers hosting that's reliable.
Audible.
Okay, thank you. Okay. So yeah, that was how you can get an entire chip made out of a speck of sand, which is actually quite fascinating. All right, let's see the entire design flow. What all happens? What I told you just now is actually a brief overview. Let's go into some details as to what actually happens. So the entire design flow is split up into two components. One is front end, the other one is back end. So what happens in front end is, like I said, the customer or the client will come up with a set of ideas and requirements, which we call as specifications. From that, we extract a golden reference through modeling, and we do a microarchitecture definition. The architecture is defined. Then we go into the design phase where we actually design it using the hardware description languages. Then it goes into functional simulation to verify the functionality if the intent has been met. Then it goes through the synthesis, wherein, like I said, it gets converted from English-like language to actual logical gates. Then there is something called as DFT, scan insertion. DFT is nothing but design for testability. What happens here is post manufacturing the chip, when it comes out, we have to still test it out to see if the functionality is still working. The reason behind this is we are dealing with transistors as small as 5 nanometers, right? So, which even a speck, one small speck of dust in the air, which is not even visible to the human eye, if it falls on the chip, it can ruin the whole chip. So because of that, we need to be extremely careful. And like you saw in the video, uh, the rooms were all lit up in yellow color, and there were people walking around in something which looked like a PPE kit, right? That's actually called as a bunny suit. So, uh, and the process where all of this takes place is called as clean rooms. So those clean rooms are impeccably clean. They should not even have specks of dust, which will uh, uh, ruin the ICs. So because of that, we need to have testing done at the after the manufacturing of the IC as well. So to enable that testing, we will be putting some hooks uh, in order to test it later. So those things are called DFT. So in any of these cases, if something is not right, if the expectation is not met, or if there is an issue or there is a bug in the design, it always goes back to the RTL design, the designers, and they have to either fix it or redo it. Do it until everything is met as per expectations. Once all of this is done, it moves to the process called backend. Now, what happens in backend? We get the synthesized netlist from the front end, and then something called timing analysis is done. This is a slightly complex procedure, but just assume that timing analysis is nothing but making sure that all the data is reaching all the places at the right time. That's the major intent behind function timing analysis. And after this also, there are more verification done. Verification is done at multiple levels, like I said. Again, if the expectation is not met, goes back to the designer. Now, once this is done, there is a procedure called as floor planning. Now, what happens in floor planning is, um, imagine you're building a house again, right? So when you are building a house, there is an architect who will first make a blueprint as to what goes where. The kitchen goes here, the living room goes here, the bedrooms are over there. So like that, we also make a floor plan as to which component goes where. So the floor planning is first done. And then post that, we place the actual components as per the floor plan and we route them. Now, what happens in route? Route is nothing but connecting each transistor to power and giving it a ground. We need something to power the transistors, right? Because that's how semiconductors work. We need to power them up. So we have to supply power rails and also give ground to each and every single transistor on the chip. So that process is called routing. Parasitic extraction. So when the conversion happens from actual English-like code to an actual transistor, there are certain parasites like resistors or capacitors that get formed which are not intended, but they accidentally get formed. So those have to be removed. So that's called parasitic extraction. And again, it goes through an equivalence check. There are some design rules which are to be followed here. So again, the equivalence, logical equivalence will be checked at this level as well. And post this also, we will have a layout, post layout verification. Now, the reason why we are doing verification at so many levels is because the whole process is very complex. If we verify at the very end, then we'll have no idea where it went wrong because it can go wrong at so many places. So at every level, we have to keep verifying if the intent is met. So once everything is done and we are about, we can never be 100% sure, we can, it's usually around 95 to 98. When we reach that level of confidence, then we um, give it out to manufacture in the form of GDS2. Now, what is GDS2? In the video, you might have seen that there are masks, right? There are some masks which are exposed to light and that goes through some lenses and actually falls on the silicon wafer. So, sorry. Yeah. Yeah. Yeah, so those masks which the video was talking about are nothing but the GDS2 formats. So we will finally hand over the masks to the fabrication units. And the fabrication units will then take those masks and follow all the procedure listed in that video. And finally, we'll be getting our chip. There's actually one more video which was shared by Intel. It was publicly shared by Intel, which actually gives you a complete overview of whatever I told so far. It's called as the life cycle of a chip again. So let's take a look at that.
Hi, I'm Chip. I'm a computer chip. I'm also called a microprocessor, but you can think of me simply as the brain that controls your computer. I'm probably the most complex product manufactured in the world, but I'm not much bigger than your fingernail. I'm packed with billions of microscopic switches called transistors that make me work. Come along with me. I'll show you my journey inside Intel, from when I'm first created to when I'm shipped to customers. Before I become the beautiful, complex square that you see, I begin as an idea in the minds of chip architects. These amazing engineers work with logic and circuit designers to create computerized drawings, which eventually become the blueprints for my transistors and layers that make up my complex circuitry. You see, I might look extremely thin, but I'm made up of about 30 layers that resemble a multi-level highway. Some of the layers form my transistors. Other layers make up the interconnects that tie my transistors together in a very specific configuration. My transistors can switch on and off up to 5 billion times per second, so your computer can complete tasks. But more on that in a bit. First, once the chip architects are happy with my design, they send their blueprints to mask engineers. Mask engineers take those digital blueprints and use an electron beam machine to convert the computer-aided design drawings into a template usable in manufacturing. The machine's electron beam takes that data and replicates the circuitry pattern onto 6 by 6 inch pieces of quartz, just a 1/4 inch thick. These quartz pieces, which we call masks, are stencil-like templates that we use later to build up the circuitry onto a silicon wafer. It can take more than 50 masks to make all my layers. As the mask engineers finish each mask, they send them to fabrication factories, or fabs, to begin manufacturing me. These huge factories are where you'll spot manufacturing technicians in those funny-looking bunny suits. And those curious pizza-sized discs are silicon wafers, made from the silicon extracted from sand. Techs take the masks and use photolithography machines to shine light through them, then through a lens to reduce the image, and then onto the surface of a wafer. They do this repeatedly, using different masks for all my different layers of transistors and wire connections. Eventually, the wafer will be imprinted with hundreds or even thousands of tiny individual chips, like me. From here, the fab sends the finished wafers to die sort prep facilities. In these facilities, diamond saws cut the wafers into thousands of fingernail-sized individual rectangles, each called a die or computer chip. Die and sort prep machines cherry-pick the working chips and then hand them off to yet another machine, which places them onto reels. These are then sent to our assembly and test plants. Here, technicians take each die and test them one last time to make sure they're healthy and good to go. If we pass, were then mounted between a substrate and a heat spreader to form a sleek enclosed package. Our exterior package protects us from getting knocked around, heat, and contaminants. Once we go inside a computer, our package also forms electrical connections between us and the circuit board. We've got just one more step before we reach customers: the finished goods warehouses. All Intel assembly and test plants have them. From here, logistics professionals send us directly to some customers, such as system manufacturers, or they ship us to global distribution hubs. From these hubs, we might be sent out to original equipment manufacturers in trays, or get boxed up nice and pretty for retail. Phew, what a journey, right? So many Intel people from around the globe working together to design, create, and deliver the tiny, amazing chips, like me. So every once in a while, give a thought to old Chip here and all of the steps it took me to get from concept to powering the computing devices you depend on every day.
All right, so that was Chip for you, which very nicely explained all the processes. Okay, moving on. All right, so lastly, let's look at the opportunities that you can find in the VLSI industry. Hello? Okay, so let's take a look at the opportunities that you can find in VLSI industry. So like I said, there are two bifurcations. There is front end and there is back end, right? So in front end, I'm just giving you the major roles, but there are a lot more roles that can be offered. Majorly, you have design engineers who work on the analog or digital or mixed signal design part. We have verification engineers who verify things at different levels. And we have DFT engineers who perform the design for testability. And then there is backend where we have physical design engineers and layout engineers who do all the processes which I mentioned in the background, like uh, uh, floor planning, place and route, and design rule check, and all of that. So we have backend engineers doing all of that. And then we have silicon validation engineers. These are the people who test the chip after it gets manufactured. So we have silicon validation engineers, and there are RF engineers as well, because most of the chips coming out now, especially chips like modem, which usually requires an RF component also to be present in the chip along with the other things. So RF engineers are not many in number, but it's a highly respected and highly appreciated job. So there are RF engineers as well. So this is a brief introduction on the opportunities that you can get in this industry. So finally, to conclude, I just want to give you 3 reasons as to why you should be choosing VLSI as your career in the future. Firstly, this is a thriving industry because, like I said, we have everything around us are electronic gadgets, and more and more are yet to come because everything around us is becoming smart. So what is the meaning definition of smart? Definition is to put some brain into something, right? And those brains are nothing but these chips which we just saw. So this is an industry which is going to flourish for years to come. So there'll not be an end to the industry because there are so many opportunities and so many things to work on. It's a thriving industry. Secondly, if you are a core electronics enthusiast, then this is a highly specialized, innovative, and challenging domain, which will be a lot of fun to work with, and it will give you an excellent career growth in your career. So this is one of the main reasons why you should be choosing VLSI. And finally, Though this supersedes the previous 2 points, I still would like to keep this third. It pays you very well. Um, when you start out as a fresher, you might not get the salary which you expect to, but as you move ahead in a very short span of time, if you are passionate about your work and if you are giving excellent productivity, then you will automatically see a drastic change, a drastic increase in your paycheck as well. So you will not be sad about choosing VLSI because you'll be happy at the end of every month with a handsome paycheck. So yeah, this was my introduction, a brief introduction into the field of electronics and semiconductors.